December 1942, somewhere over the Solomon Islands, a 19-year-old waist gunner named Eddie Kowalski stands in the belly of a B-17, hands gripping a Browning M2 that's vibrating like a jackhammer. A Japanese Zero slides into view at his 10 o'clock, maybe 300 yards out, moving left to right across his field of vision like a dart. Eddie does exactly what every instinct in his body tells him to do. He puts the crosshairs directly on the enemy plane's fuselage and squeezes the trigger. 50 rounds scream out. Tracer fire arcs through the air, and Eddie watches every single bullet pass harmlessly behind the Zero's tail. The Japanese pilot doesn't even flinch. He just keeps flying, completely untouched, while Eddie's ammunition counter spins down toward empty. This wasn't Eddie's failure. This same scene played out thousands of times across every theater of World War II during those early years. American gunners, well-trained, motivated, equipped with the finest machine guns ever built, were missing. Not occasionally, constantly. In early 1943, the Army Air Forces conducted a study analyzing gun camera footage from bomber missions over Europe and the Pacific. The results were catastrophic. Trained aerial gunners were achieving hit rates below 4% against crossing targets. 4%. That means for every 100 rounds fired at an enemy aircraft, moving perpendicular to the gunner's position, 96 bullets missed entirely. The math was brutal. A typical engagement lasted only 8 to 12 seconds before the enemy fighter broke off or moved out of range. The Browning M2 fired roughly 800 rounds per minute, about 13 rounds per second. In a 10-second fight, a gunner could theoretically fire 130 rounds. With a 4% hit rate, only 5 bullets might actually strike the target. 5 hits weren't enough to bring down a Zero, let alone a rugged aircraft like the Focke-Wulf WWII German and Japanese fighters could absorb dozens of 50 caliber rounds and keep flying. The human cost was staggering. In 1943 alone, the 8th Air Force flying over Europe lost 188 bombers per month on average. Each B-17 carried 10 men. That's 180 air crewmen killed, captured, or missing every 30 days, and a significant percentage of those losses came from bomber formations that couldn't effectively defend themselves. Against fighter attacks, the gunners were doing everything right by all accounts. Tracking the target, maintaining sight picture, controlling their bursts. The problem wasn't courage. It wasn't commitment. The problem was physics, and physics didn't care about bravery. Every gunner instinctively aimed directly at what they could see. It made perfect sense. You point at the thing you want to hit. You pull the trigger. The thing gets hit. That logic works fine when you're shooting at a stationary target on a rifle range, or even hunting a deer moving at 20 miles per hour. But enemy fighters weren't deer. They were crossing the gunner's field of view at speeds exceeding 300 mph. Some late war models like the Messerschmitt Me 262 jet could hit 540 mph at those velocities. The time it took for a bullet to travel from the gun muzzle to the target's position meant the target wasn't there anymore by the time the bullet arrived. The bullet itself moved fast, roughly 900 feet per second, leaving the barrel of a Browning M2. That sounds instantaneous, and at short ranges against slow targets it effectively was. But in aerial combat, short range meant 200 to 400 yards, and the targets were screaming through the sky at speeds that would have seemed impossible just 20 years earlier. Zero flying at 300 mph covered 440 feet every single second. Do the math on a 300-yard shot. That's 900 feet. At 2,900 feet per second, the bullet needed roughly 0.31 seconds to cover that distance. Doesn't sound like much, does it? But in those 0.31 seconds, that Zero moved another 136 feet forward, 11 car lengths. The gunner aimed at where the aircraft was. But the bullet arrived at where the aircraft had been a third of a second ago, passing through empty air while the enemy fighter continued unscathed. This phenomenon had a name: deflection error. Military scientists understood it in theory long before World War II, but understanding something in a classroom and solving it in combat were entirely different problems. The deflection required wasn't some minor adjustment. It was massive and counterintuitive. Against a target crossing at 90 degrees at 300 yards, a gunner needed to aim approximately 15 to 20 feet ahead of the aircraft's nose. That meant putting your crosshairs on what looked like completely empty sky. trusting that the target would fly into your stream of bullets. Every human instinct screamed against it. Gunnery instructors tried teaching deflection shooting during training, but the results were dismal. The Army Air Force's Flexible Gunnery School at Laredo, Texas, put students through rigorous programs starting in 1942. Trainees spent hours in turret simulators, shot at towed targets from moving trucks, studied diagrams showing proper lead angles. None of it translated effectively to real combat. The problem was, complexity deflection wasn't a single calculation. It changed constantly, depending on target speed, target angle, range, altitude, whether the target was climbing or diving, whether your own aircraft was turning. B-17 ball turret gunner engaging a Bf-109 making a frontal attack needed different deflection than the same gunner engaging the same aircraft during a beam attack from the side, and he had maybe 4 seconds to process all those variables while being shot at, while his aircraft bucked through flak damage, while his oxygen mask fogged up at 25,000 feet. The psychological barrier was just as deadly as the technical one. Gunners who survived their first few missions and tried implementing deflection shooting often abandoned it after apparent failures. They'd aim ahead of a target, fire a burst, see their tracers arc through empty sky in front of the enemy plane, and conclude they'd led too much. Next engagement, they'd reduce their lead, moving their aim point closer to the visible target. They were self-correcting in exactly the wrong direction, trusting their eyes over the physics they couldn't see. Gun camera footage from 1943 mission shows this pattern repeatedly. Initial bursts with some forward lead, followed by subsequent bursts walking backward until the gunner was shooting directly at, or even slightly behind, the target's current position. The casualties, mounted. 8th Air Force records from October 1943. Missions to Schweinfurt showed 20% losses. 60. Bombers failing to return out of 200. 91 dispatched. The survivors landed with dead and wounded crewmen, shredded hydraulic lines, engines trailing smoke. In debriefings, gunners reported the same frustration. They'd been shooting, their guns had been working, but their bullets hadn't connected. Something fundamental had to change, and it had to change fast, because at the current loss rates, the Allied bombing campaign would collapse before it ever reached Berlin. The solution had been sitting in a filing cabinet since 1924, written by a man most combat air crews had never heard of, Lieutenant Colonel James Puckle, not the historical inventor of the Puckle gun, but an American artillery officer with a gift for ballistics. He published a technical paper titled The Problem of Lead in Aerial Gunnery while serving as an instructor at the Army's Field Artillery School. Puckle wasn't some theoretical academic, disconnected from reality. He'd served in France during World War I, witnessed the first clumsy attempts at air-to-air combat, and recognized that aviation speeds were about to create a targeting crisis that traditional marksmanship couldn't solve. His paper laid out the mathematics with brutal clarity. Puckle demonstrated that as aircraft speeds increased beyond 150 mph, the deflection angles required would exceed human intuitive capability. He calculated that against a target moving at 250 mph at a perpendicular angle, a gunner would need to aim approximately 4 to 5 aircraft lengths ahead of the visible target. His paper included tables, exhaustive charts showing required lead for various combinations of target speed, range, and crossing angle. A 200-yard shot at a 90-degree crossing angle against a 300 mm target. Lead 47 feet, same target at 400 yards. Lead 94 feet. The numbers were staggering, and Puckle's conclusion was even more disturbing. Without mechanical assistance, aerial gunners would be effectively useless within a decade. The Army filed his paper and forgot about it. Throughout the 1920s and 1930s, military aviation advanced rapidly, but gunnery training remained rooted in World War I methodology. Instructors taught marksmanship fundamentals, sight picture, trigger control, breath control, as if students were preparing for a rifle competition, not a three-dimensional chase at 300 mm. The few voices advocating for advanced deflection training were dismissed as alarmists. After all, the reasoning went, Americans had always been excellent marksmen. Daniel Boone, Sergeant York, the frontier tradition of sharpshooting. Surely those skills would translate to aerial combat with proper practice. They didn't. When the United States entered World War II in December 1941, the Army Air Force's gunnery training was catastrophically unprepared for the reality of modern air combat. The standard training program lasted 4 weeks. Students fired roughly 1,000 rounds total during their entire qualification course. Most of that ammunition went toward stationary targets and slowly towed sleeves moving at maybe 150 mph in predictable straight lines. Not a single training scenario replicated the chaos of an FW-190, diving through a bomber formation at 400 mph while executing a barrel roll. Graduates received their wings, climbed into bombers, flew to England or the Pacific, and discovered their training was worthless the first time a zero flashed across their gun sight. By mid-1942, desperate commanders started digging through old technical libraries, looking for anything that might help. A captain named Robert Williams, assigned to the 8th Air Force Gunnery Analysis Section, found Puckle's 1924 paper in the archives at Wright Field. Williams read it in one sitting, then immediately drafted a memo to his commanding officer. With 2 words underlined 3 times, he knew. Puckle had predicted this exact disaster 18 years before the first B-17 ever flew a combat mission over Europe. His calculations were still accurate, his warnings had been correct, and hundreds of American air crewmen had died because nobody had listened. The question wasn't whether Puckle had been right. The mathematics were indisputable. The question was, could anything actually be done about it? Training gunners to consciously calculate deflection angles while being shot at seemed impossible. The human brain couldn't process trigonometry at combat speed, but if conscious calculation wouldn't work, maybe something else would. Enter the British. They'd already started finding answers, born from the same desperation during the summer of 1940. RAF Squadron 609, flying Spitfires out of Middle Wallop, faced a gunnery crisis that mirrored what American bombers would encounter 2 years later. Their pilots were brave. Their aircraft were magnificent, but they were missing. Flight Lieutenant I. John Dundas reviewed gun camera footage from July engagements and discovered his squadron's hit rate against crossing BF-109s was hovering around 6%. 6 shots connecting out of every 100 fired. The Spitfire carried enough ammunition for roughly 16 seconds of sustained fire. Pilots were burning through their entire combat load and watching German fighters fly home untouched. Squadron leader Horace Derry made a radical decision. He grounded his entire unit for 3 days in early August 1940, right in the middle of the Battle of Britain, when every fighter was desperately needed in the air, and conducted live-fire experiments that violated every standard in the RAF training manual. Derry had been a competitive clay pigeon shooter before the war, and he understood something about leading moving targets that military theorists had overlooked. The best shotgun shooters didn't calculate lead, they felt it. Their brains processed the target's movement subconsciously. Their hands moved the barrel ahead of the clay disc, without conscious mathematical thought. Derry wondered, could fighter pilots learn the same instinctive response? His experiment was brutally simple. He had a Hurricane fighter tow a target banner across the gunnery range, while his Spitfire pilots made repeated firing passes. But instead of the standard approach, aiming carefully, trying to calculate the precise lead angle, Derry instructed them to do something that sounded insane. Don't aim at all. Instead, watch the target's movement. Let your eyes track its path. Start firing while your aircraft is still turning to follow. Let the deflection happen naturally through the motion of your turn, rather than trying to consciously create it with aiming adjustments. Fire into where your instincts say the target is going, not where your eyes say it currently is. The first attempts were disasters. Pilots missed the banner by 50 feet, their bullets stitching patterns across empty sky. But Derry made them repeat the exercise. Again. 30 passes each over 3 days. No lectures about ballistics. No trigonometry, no tables of deflection angles. Just repetition, with one simple instruction: fire while you're still moving. Not after you've steadied on target. By the 3rd day, something remarkable happened. The pilots' hit rates began climbing, not dramatically. from 6% to maybe 12%, but that doubling meant twice as many bullets hitting German aircraft, which meant twice as many kills, or twice as many damaged enemy fighters returning to base unable to fly the next mission. Derry documented his results and submitted them to Fighter Command Headquarters on August 18, 1940. His report included a crucial observation. The pilots who improved fastest weren't the ones with the best peacetime marksmanship scores. They were the ones who could suppress their instinct to aim carefully and instead trust their peripheral vision and motion sense. The conscious brain, Derry argued, was too slow for modern air combat. The answer was training the subconscious to handle deflection automatically, the same way a baseball player's brain calculates where a fly ball will land, without consciously solving trajectory equations. Fighter Command circulated Darley's findings, but implementation was scattered and inconsistent. Some squadrons adopted the technique enthusiastically, others dismissed it as unscientific nonsense. The RAF's training command was particularly resistant. Their instructors had decades of experience teaching marksmanship fundamentals. Darley's approach seemed to abandon everything they knew about proper shooting discipline. But combat results didn't lie. Squadrons that embraced motion-based deflection shooting showed measurably better kill ratios through the autumn of 1940. The data was clear enough that by early 1941, the technique was quietly becoming standard practice, even if official manuals hadn't caught up yet. American military observers in Britain took detailed notes on Darley's methods. But the United States Army Air Forces faced a different problem. Fighter pilots could potentially learn instinctive deflection through repetition, but bomber gunners couldn't. A Spitfire pilot controlled his entire aircraft using motion and angles to create natural lead. A waist gunner in a B-17 stood in a fixed position while his aircraft flew straight and level through flak, unable to maneuver, unable to use aircraft movement to generate deflection. He had only his hands on the gun and his eyes on the target. If conscious calculation was too slow and instinctive motion wasn't available, the solution had to be mechanical. Enter the Massachusetts Institute of Technology. Specifically, the Radiation Laboratories Division 7, established in early 1942. The name was deliberate misdirection. Radiation Laboratory suggested atomic research, which helped maintain secrecy around what Division 7 actually built, fire control systems. The head of the division, Dr. Charles Stark Draper, was a 40-year-old engineer who'd spent the previous decade developing gyroscopic instruments for aircraft navigation. Draper understood that the deflection problem wasn't fundamentally about shooting, it was about prediction. A gun sight needed to show the gunner not where the target currently was, but where the target would be when the bullets arrived. The Mark I-14 computing gun sight emerged from Draper's lab in prototype form by July 1943. It looked like something from science fiction, a reflector sight connected to a gyroscope system that weighed 28 pounds and required electrical power from the aircraft's generator. The gunner operated it through a mechanical ranging control. He turned a dial to match reference marks to the target's wingspan, giving the sight the range information it needed. Then he tracked the target for approximately 2 seconds, keeping it centered in a small tracking circle. During those 2 seconds, the gyroscope measured the target's angular velocity, how fast it was moving across the gunner's field of view. Here's where it got remarkable. The Mark I-14's internal mechanism used a series of cams and gears, analog computers built from machined metal, to solve the deflection equation in real time. It took the range input from the gunner, the angular velocity from the gyroscope, and the known ballistic properties of the .50 caliber round, then calculated exactly how far ahead of the target the guns needed to point. It displayed the result as a glowing reticle that appeared to float in space, ahead of the target. The gunner didn't aim at the aircraft anymore. He aimed at the glowing dot, and if he'd ranged correctly and tracked smoothly, the dot showed him exactly where to shoot. The Mark I-14 solved mathematics that would take a human brain several minutes using pencil and paper, and it solved those equations 30 times per second, continuously updating as the target's angle and range changed. Testing at the Naval Air Station in Norfolk, Virginia, during August 1943, produced results that seemed almost impossible. Gunners who'd never achieved better than 5% hit rates against crossing targets jumped to 18% on their first day using the system. After a week of practice, rates climbed above 25%. That was a 5-fold improvement over manual aiming. WWII. Production didn't begin in meaningful numbers until early 1944, and installation priority went to new aircraft rolling off assembly lines, not retrofitting existing bombers. That meant the majority of gunners flying missions through late 1943 and early 1944 were still using basic iron sights or crude reflector sights with no computing ability. They needed something they could implement immediately, without waiting for new technology, without requiring electrical modifications to their aircraft. They needed a technique that worked with the equipment they already had. The breakthrough came not from engineers or scientists, but from combat gunners themselves, specifically from the Pacific Theater, where engagement distances and visibility were often better than over cloud-covered Europe. Staff Sergeant William Bill Fleming, a waist gunner aboard the USS Lexington's Air Group Support Staff, had flown 31 combat missions by March 1944 and survived 4 aircraft losses. Fleming wasn't an officer, didn't have a college education, couldn't explain gyroscopic precession if his life depended on it, but he'd fired approximately 40,000 rounds in combat and had personally witnessed hits on 7 enemy aircraft. He'd also kept a notebook. Fleming's notebook contained something unusual: sketches of enemy aircraft with hand-drawn lines extending forward from their noses, showing where he'd actually aimed during successful engagements. He'd measured these lead distances by comparing them to the target aircraft's length, 2 plane lengths ahead or 3 plane lengths ahead. On March 14, 1944, Fleming presented his notebook to Lieutenant Commander Edward Butch O'Hare, already a Medal of Honor recipient and one of the Navy's top tacticians. O'Hare immediately recognized what he was seeing: empirical deflection data gathered under actual combat conditions. O'Hare ordered Fleming to conduct training sessions with every gunner in the air group, not classroom lectures. Practical exercises using a simple technique that became known as the spot shooting method. Fleming would have gunners stand at their positions while another crew member walked along the flight deck holding a model aircraft on a pole. As the model flew past at various angles, Fleming coached gunners to extend their aim forward by specific increments: 1 aircraft length for slight crossing angles, 2 lengths for moderate angles, 3 or more for steep crossing shots. The key? Giving gunners a visual reference they could remember and apply instantly. Count plane lengths forward from the nose, then fire. The Lexington's gunnery officer, skeptical but desperate for anything that might work, authorized controlled testing during the carrier's operations off Truck Lagoon in late March 1944. He pulled ammunition expenditure and hit confirmation data for the previous 8 weeks, then tracked the same metrics after Fleming's training program. The results were undeniable. Prior to training, 4.2 hits per 100 rounds fired against crossing targets. By the end of April, just 6 weeks after implementing spot shooting, 9.1 hits per 100 rounds. The technique had more than doubled their effectiveness. Word spread through the Pacific Fleet with remarkable speed. By May 1944, variations of Fleming's spot shooting method were being taught aboard the carriers Essex, Enterprise, and Bunker Hill. Each carrier's gunnery officers added their own refinements, but the core principle remained: give gunners a simple visual measurement system tied directly to the target's apparent size, eliminating the need for conscious calculation. A gunner didn't need to know he was compensating for 0.3 seconds of bullet flight time. He just needed to remember 3 plane lengths forward for a crossing shot. The technique worked because it matched how human visual processing actually functions. Our brains are exceptional at relative size comparison, but terrible at absolute distance estimation. Asking a gunner to lead by 50 feet meant nothing when he had no reference for what 50 feet looked like at 300 yards. But led by 2 plane lengths gave him an immediate visual standard he could apply without thought. The 0 he was tracking provided its own measuring stick. He just had to extend that measurement forward into empty space. The Army Air Forces adopted similar training protocols by mid-1944, though they called it radius of action shooting. Technical manuals started including illustrations showing proper lead distances expressed in multiples of target wingspan or fuselage length. The 8th Air Force Gunnery School at Lavenham, England, rebuilt their entire training program around the technique during June 1944. Mission loss rates, while still significant, began declining. July 1944 showed 3.4 to 4.4% bomber losses per mission, compared to 5.2% the previous October. That difference represented hundreds of crew members who flew home instead of dying over Germany. But knowing the technique and executing it under combat conditions remained two entirely different challenges. The human brain, even armed with the spot shooting method, still fought against itself when the shooting started. Psychologists embedded with the Army Air Forces documented this phenomenon extensively during 1944 interviews with returning gunners. The issue wasn't knowledge. Gunners could recite the proper lead distances perfectly during debriefings. The issue was that conscious knowledge evaporated under stress, replaced by primal instinct that screamed, "Aim at the threat." Captain Harold Klein, an Army psychologist stationed at Bovington, studied this response through analysis of gun camera footage paired with post-mission interviews. He identified a pattern he termed threat fixation collapse. Gunners would start an engagement using proper deflection, but as the enemy fighter closed and the perceived danger intensified, their aim point would progressively drift backward, until they were shooting directly at, or even behind, the target. Klein's data showed this collapse happened fastest during head-on attacks where the closing speed between bomber and fighter exceeded 500 mph, and the gunner had perhaps 2 seconds before the enemy opened fire. Under that extreme stress, rational technique dissolved into pure reaction. Point at the scary thing. Pull trigger. The only solution? Repetition so extensive that deflection shooting bypassed conscious thought entirely, embedding itself at the same neurological level as walking or catching a thrown ball. This required training time the military couldn't afford in 1942 and 1943. But by late 1944, with Allied control of the air improving and training pipelines more established, gunnery schools extended their programs. The standard course that had been 4 weeks in 1942 expanded to 8 weeks, then 10. Students now fired 5,000 rounds during training, instead of $1,000. And significantly, over half of those rounds went toward moving targets at realistic combat speeds. The Naval Air Gunner School at Jacksonville, Florida, pioneered a particularly effective drill starting in August 1944. They mounted 50 caliber guns on motorized turrets that could spin and elevate rapidly, then had high-speed boats tow targets across the water at speeds up to 60 mph, while varying their distance and crossing angles randomly. Gunner trainees engaged these targets repeatedly, 50 to 70 passes per day, until the act of leading became automatic. Instructors didn't correct students verbally during the drills. They simply had them shoot, check their hit pattern, adjust, and shoot again. The subconscious learned through feedback loops, faster than the conscious mind learned through instruction. Elite gunners who survived 30 or more missions demonstrated something remarkable in combat footage analysis. Their deflection aim points remained stable, even under intense stress. When an FW-190 came screaming through the formation with cannon, fire flashing from its wings, these experienced gunners maintained their lead automatically. Their conscious minds could be terrified. Many admitted to being absolutely convinced they were about to die during certain engagements, but their hands kept the proper sight picture anyway. They'd achieved what martial artists call mushin, or no mind, the state where technique happens without conscious direction. But that level of proficiency took time and ammunition most gunners never received. The mathematics of wartime training were brutal. If creating an expert deflection shooter required 5,000 practice rounds and 10 weeks of intensive training, but the bomber offensive needed 50,000 new gunners in 6 months. Compromises were inevitable. The majority of gunners flying combat missions never achieved true unconscious competence. They remained perpetually in the conscious competent stage, capable of proper deflection shooting when conditions allowed them time to think, but vulnerable to collapse under extreme stress or unexpected tactical situations. This created a strange stratification in combat effectiveness. A bomber formation's defensive firepower wasn't uniform. It depended heavily on which specific gunners were in which specific positions on which specific aircraft. A formation that happened to include several veterans with deep training could fight off attacks that would devastate a formation of newer crews. German fighter pilots learned to identify and exploit this. They targeted bombers that showed hesitant or inaccurate fire during initial passes, avoiding formations where the defensive fire was immediate, heavy, and precisely placed. The deflection, shooting revolution, born from British experiments and American desperation, didn't end when World War II concluded in 1945. The core principle, that you must aim where the target will be, not where it is, became foundational to every weapon system developed afterward. The Mark I 14 computing gun sight evolved into the Mark I 18, serving. An AIM-120 AMRAAM missile uses inertial guidance and active radar to continuously update its trajectory toward where its target will be, executing deflection calculations thousands of times per second. The F-22 Raptor's AN/APG-77 radar doesn't just track targets. It predicts their future positions based on current velocity and acceleration, then positions the aircraft and selects weapons accordingly. It's the same problem William Fleming solved with hand-drawn sketches in 1944, now handled by computers, processing teraflops instead of gunners counting plane lengths. Interestingly, deflection shooting fundamentals remain part of modern fighter pilot training. Despite guns being tertiary weapons in contemporary air combat, the Navy Fighter Weapons School, Top Gun, still teaches basic fighter maneuvers that include guns-only engagements. Not because pilots expect to dogfight with cannons, but because learning to visually predict where a maneuvering target will be develops spatial awareness that applies to every aspect of air combat. A pilot who's mastered deflection shooting intuitively understands closure rates, angle off, and lead pursuit curves, concepts that matter whether you're firing a cannon or positioning for a missile shot. The lessons extend beyond aviation. Modern anti-aircraft systems, from the Phalanx CIWS defending naval vessels to the CRAM protecting ground bases, are essentially sophisticated implementations of what those 1943 bomber gunners struggled to do manually. The Phalanx fires 4,500 rounds per minute, 75 rounds per second at incoming missiles and aircraft, its radar continuously calculating deflection and updating aim point. It makes the same corrections Eddie Kowalski needed over the Solomon Islands, just faster, and without the human hesitation that costs so many lives. Even video games that simulate combat incorporate deflection mechanics, teaching players the same counterintuitive principle: aim where the target is going. Games like War Thunder and Digital Combat Simulator require players to lead moving targets manually. New players experience the exact same frustration 1942 gunners felt, watching their tracers pass harmlessly behind enemy aircraft until they internalize that leading is necessary. The most skilled players develop the same unconscious competence that combat veterans achieved, their hands adjusting aim without conscious thought. The transformation from 4% hit rates in early 1943 to 20% plus by late 1944 represents one of the most dramatic tactical improvements of World War II, achieved not through superior equipment or overwhelming numbers but through understanding and working with human cognition rather than against it. Thousands of aircrewmen who would have died continued flying. Enemy fighters that would have escaped went down in flames. Bombing campaigns that might have failed reached their targets. All because someone finally acknowledged human instinct, however strong, could be wrong. And survival meant training people to ignore what felt natural and trust what physics demanded. The gunners who learned to aim at empty sky forced themselves to fire at nothing visible and trusted their bullets would meet metal, proved something essential about human adaptability under pressure. We're not prisoners of our instincts. With proper understanding, sufficient training, and enough desperation, we can rewire our responses to match reality, rather than demanding reality match our intuitions. That lesson, born in blood over Europe and the Pacific, remains relevant anywhere humans confront a world where instinct and solution point in opposite directions.